Welcome to Introduction to Soils, Part 1, Soil and Soil Development. This is the first lecture in a two-part series intended to provide a crash course in soil science and introduce key concepts related to soil health. In this lecture, we'll talk about what soils are and what they are made of, learn about how soils develop, and the important soil forming factors here in Vermont, as well as local land use history. Let's start with a definition. What is soil? Soil is a natural body of mineral and organic matter at Earth's surface, and it's the zone where chemical, physical, and biological processes all interact. Soil performs many critical ecosystem services, including water storage, nutrient cycling and retention, water filtration, carbon sequestration, and supporting biodiversity. Soils are generally about 50% mineral and organic matter, or the actual stuff. We'll talk more about where that stuff comes from and what it is. The other 50% of soil is space. We call the space in between soil particles pores, and those pores can be filled with either water or air. Looking at the stuff in soil, we have mineral particles, which make up about 95% of soil matter, and organic matter, which is a much smaller percentage, about 5%. The mineral particles that make up soil were originally part of bedrock somewhere on Earth. Minerals can come from direct weathering of the bedrock in place underneath the soil, but they can also be transported. Glaciers, wind, water, and gravity all move materials around. The organic matter in soil comes from plants, and it can also come from soil organisms like bacteria, fungi, microarthropods, nematodes, and earthworms. All of these organisms live and eventually die in the soil. The material making up their body decomposes, and some of that can end up being preserved in soils over long timescales and provide important functions for the soil. It's important to understand that soils are dynamic and they change throughout time. This slide is showing a 30,000-foot view of how soils develop over time. As soils age, the particles begin to aggregate or come together, and they form distinct structures. Over time, the physical, biological, and chemical properties of soil develop. As this development proceeds over time, soils develop distinct horizons. Next, we're going to talk about the physical, biological, and chemical processes that cause these changes to happen. The first very major process that influences soil is the addition of material. Additions can come from dust particles transported by the wind, rainfall carrying dissolved chemicals, plant litter falling off of plants and getting deposited on the surface, microbial growth within the soil, or dissolved chemicals percolating up through the groundwater. All of these processes bring something into the soil that wasn't there before. Also lose material. This can happen through wind or water erosion, or through leaching losses, in which dissolved chemicals in soil are lost as the water moves downwards through the profile, bringing those chemicals with it. There are also processes of both transformation and transport that take place within the soil. Transformation processes include chemical weathering, which we'll look at in a second, as well as redox cycling, which can happen because of wet-dry cycles. Transport also happens within a soil profile. Very broadly, any chemical compound that can be dissolved in water can be transported downwards and then reprecipitate as a solid mineral lower down in the subsoil. We're going to talk about transport in greater depth soon. It's also important to remember that soils are alive, so biocycling can take place. This happens when plants and other soil organisms take up key soil nutrients like calcium and magnesium and remove them from the soil profile, and then redistribute those materials through their residue and roots. Organisms also respire carbon dioxide, which dissolves in soil water to make carbonic acid and is very important in chemical weathering. And now on transformations and transport. Chemical weathering of primary minerals is one of the most important soil transformation processes, so we're going to look at that in greater depth. Some definitions to start us off. Primary minerals are the minerals that were originally formed in rocks. When those minerals chemically weather, they become secondary minerals, which we also call clay minerals. Overall, soils are clay factories. And what I mean by that is that a lot of weathering takes place in soils, and as that weathering of the primary minerals takes place, clay minerals, those secondary minerals, get produced. The chemical reaction on this slide shows the weathering of feldspar, a common primary mineral, to kaolinite, a clay mineral. This is the single most common weathering reaction on the planet. In addition to producing kaolinite, this reaction also frees up the potassium contained within the feldspar, which then becomes available for plant uptake. This means that mineral weathering is also an important source of plant nutrients. A question that I want you to think about: where do you think the acid for chemical weathering might come from? We'll come back to this question later on in this lecture. Transport is also an important process. There are two parts to transport, and they have almost the same name, which is incredibly confusing. Eluviation, spelled with an E, refers to the downward transport of soluble or suspendable compounds in water. Those compounds can be organic matter, metals, oxides, or clays. Eluviation, with an E, is whenever what's being dissolved and transported reprecipitates and accumulates in the subsoil. Overall, these two processes lead to the redistribution of materials throughout the soil profile, removing materials from higher in the profile and bringing them deeper into the subsoil. This is a really important set of processes for causing the development of those distinct horizons or layers in the soil. The photo on the slide shows a very dramatic example of an eluviated horizon, which is very lightly colored, above the much darker illuviated horizon, where the washed out compounds from above have accumulated. As these processes of addition, loss, transformation, and transportation change a soil, the soil will develop distinct horizontal layers. We call these layers horizons, and they can be differentiated by each other by differences in color, texture, structure, and other soil properties. We're going to get into these soil properties in the next lecture. The main soil horizons are the O, A, E, B, and C horizons, and not all soils are going to have all of these horizons. The O horizon is at the surface and consists of organic matter like plant leaves that haven't yet broken down completely. The A horizon is the mineral soil that is closest to the surface. It's often very rich in organic matter from the decaying plant material above. Over time, this horizon can lose iron, clay, aluminum, and organic compounds due to eluviation. The E horizon, which is not present in all soils, is a horizon where clay minerals and other chemical compounds have been severely depleted through downward leaching. This horizon tends to be very lightly colored because of those leaching losses of the pigmented compounds. The B horizon is the subsoil, and it's the zone where all of those leached clays, aluminum, iron oxides, and sometimes certain organic compounds will accumulate. The C layer consists of partially broken up or partially weathered bedrock. And then the R layer is the deepest, and it's the bedrock itself that has not yet been broken up into anything that we would understand as soil. These processes of additions, loss, transformation, and transport don't act on soils in the same way everywhere. We know this because soils look really different all around the world, and they have different properties. And so it follows that the processes that shape these soils must be acting in slightly different ways. The concept of the soil forming factors offers a way to think about where these differences come from. The soil scientist V.V. Dokuschev and later on Hans Jenny came up with this concept of the soil forming factors in order to explain the differences that they saw in soils experiencing different conditions. This equation shows that the state of a soil is a function of these 5 different factors. We call these the state factors, and they are climate, organisms, parent material, relief or topography, and time. And while it's not an official state factor, human land management has an incredible influence on soil that cannot be overlooked. So we'll talk about that as well. The state factor is climate. Climate is incredibly important because soils weather faster in warmer, wetter climates where there's more energy available for chemical reactions and there's more water available to transport the ions that cause these chemical reactions. Warm, wet conditions also support plant growth, which can increase the inputs of organic matter and carbonic acid to a soil. Cold conditions can make decomposition go more slowly, so you can end up with more organic matter accumulation, which is very important in the development of organic soils like those found in wetlands. The diagram on the slide shows how climate can influence soil development. Overall, we expect to see the most soil development in warm, wet conditions. Here in Vermont, we tend more towards the cold and wet conditions, which is really conducive to organic matter accumulation and can help explain the relatively high amount of organic matter found in many Vermont soils. State factor is organisms. Organisms matter a lot because they're the source of organic matter, and organisms are also largely responsible for important decomposition and nutrient cycling processes. Typically, the more plants that are growing, the more organic matter a soil will have. Plant roots and depth of rooting also help determine the depth of organic matter accumulation. We tend to see the deepest, richest soils in native grasslands and prairies, where the roots of the plants are very deep. Soil organism respiration also produces carbon dioxide, which dissolves in soil water to make carbonic acid and participates in mineral weathering reactions. So the presence of an active soil biology also contributes to soil weathering and development. The diagram on the slide shows different soil horizons and the depth of organic matter accumulation in different ecosystems based on their biology. I want to call your attention to the rightmost image showing a forest, because this is a really common scenario here in Vermont. We have a lot of forests and even more areas that used to be forests. Forests produce foliage that is pretty acidic, and when trees drop their needles and those needles decompose on the forest floor, it causes organic acids to build up in the surface horizon. These acids can essentially act as a claw, and they attach to iron and aluminum in the surface soil. This whole organic matter-metal complex is then transported downwards in soil solution. This gives rise to a whitish E horizon, where the humus, iron, and aluminum have all been lost. These compounds all accumulate lower down in the subsurface, so we get a really dark B horizon below the E horizon, with lots of accumulation of iron, aluminum, and organic matter. Soils where this process happens are called spodosols, and they are one of the most common soil types here in Vermont. The next state factor is landscape relief or topography, which are 2 different words for the same thing. Relief influences a variety of processes, including addition, loss, and transformation. For example, steep slopes tend to erode very quickly, which causes loss of soil material and can reset the clock on soil development. Relief also feeds back to affect climate. South-facing slopes tend to be warmer and drier in the northern hemisphere, and that's going to affect biology and chemical weathering. The hill slope model is shown on the diagram on this slide, and it can be a helpful concept for understanding how relief influences soil across a landscape. The curve represents a cross-section of a hill. At the summit, where it's very flat, soils don't erode as much. Soils on the shoulder slopes and back slopes, so the convex parts of the slope, tend to get eroded, and so those soils will be relatively thinner. Soils at the foot slope and toe slope, or the concave parts of the slope, are going to receive these eroded materials and are the zones of deposition. You can imagine that this model and the soils that result from these processes is also going to affect water drainage. Looking at the diagram, do you think that the shoulder slope or the toe slope soils will have better water drainage? Why? The next factor is parent material. Parent material matters because different types of rocks have different textures, as well as different chemical composition of the minerals, and both of these things will affect mineral weathering and the soils that form from these minerals. The diagram on the right shows the range in grain size and chemical composition of some major types of minerals found in soils. In terms of chemical composition, felsic or sialic materials tend to have more silica and aluminum and will be more acidic than mafic materials, which have more magnesium and iron and tend to be more alkaline. Different minerals also differ in how weatherable they are. Felsic materials will be more resistant to weathering than mafic minerals. Minerals also have different textures, which will further influence weathering rates. Fine-grained minerals tend to weather more rapidly due to their higher surface area available for weathering reactions. Parent material doesn't have to be bedrock. It can also be material that's been deposited on the landscape, such as river sediments or glacial till. These deposited materials can have different textures and chemical compositions, which will then affect the soils that form from them. The official state factor is time. Time is the secret sauce that integrates all other state factors. Most of the processes that we've been discussing happen fairly slowly. Over time, soils develop, the biology of ecosystems changes, weathering happens, chemical transformations take place, and soils may receive new deposits of parent materials or experience erosion or flooding, causing loss of material. You might think that all soils currently on Earth should be the same age, but they're not. Glaciation is one major geologic event that's influenced soil age all around the world. The movement of glaciers across the Earth's surface essentially scraped across the land, removing soils and depositing new materials in the areas where the glacier moved away from. Soils in areas that have never been glaciated, such as the tropics, are much, much older than soils in previously glaciated areas. Here in Vermont, the last glaciers receded about 13,000 years ago, which you can see on the geologic timeline shown on the screen. So essentially none of our soils are older than that. Additionally, inputs of new materials from deposition or loss of materials from erosion can reset soil development. So many of our soils in Vermont are younger than 13,000 years due to this process of deposition and erosion. And lastly, I want to talk about the human factor, because how we manage the land has incredibly important implications for how soil development. I think that it's helpful to understand a little bit about agricultural history here in Vermont, because that has definitely been influenced by our soils as well as influenced how our soils have developed. And I just think it's interesting. We're going to jump back to the end of the last glaciation, about 13,000 years ago. Vermont has been Abenaki homeland since time immemorial, and evidence of settlement on the shores of what we now call Lake Champlain date back to at least 13,000 years ago, so basically as soon as the glaciers receded. The lake was a center of trade between nations, and Abenaki people engaged in many agricultural activities, as well as maple sugaring, hunting, and fishing. Some of the key crops included corn, beans, squash, sunflower, Jerusalem artichoke, ground cherry, and tobacco. It's also worth noting that Abenaki language includes many different words for classifying soils, indicating a very nuanced and detailed understanding of soil science. Colonization hit Vermont in the 1600s. In 1609, Samuel de Champlain came to Vermont and claimed northern Vermont for France. This set off a period of both French and British colonization of the state, during which time wars and genocide were waged on the Abenaki people. Colonists established small farms across the state and were mostly engaged in subsistence farming. Agriculture remained at a subsistence scale for a long time, but began to scale up around 1790, when the establishment of shipping routes made larger scale export agriculture possible, and colonizers began clearing forests to produce potash and pearl ash, and also produce potatoes, grains, and beef cattle for export. Export agriculture set off a period of widespread deforestation of Vermont. By the 1800s, about 80% of Vermont had been cleared of its trees. Most of the land below 2,500 feet in elevation was cleared during this time. This happened both because of the demand for forest products and because cleared forests could then be used for pastures. This pasture land became especially important during the 1830s and 1840s, when the price of merino wool was very high, and Vermont settlers were raising sheep at a massive scale during a time known as the merino wool craze. The wool craze didn't last forever. By the late 1800s, the price of wool dropped, and Vermont's wool industry collapsed. Farmers switched to dairy and got into producing butter and cheese, as well as maple sugar, hops, livestock, diversified produce, and lumber. In the 1890s, the Franklin County Creamery Association in St. Albans was the largest butter factory in the world, which I think is a pretty fun fact. In the later part of the 1800s, people started to think that maybe deforesting the state on a massive scale wasn't such a great idea. By 1909, Vermont appointed its first state forester, which marked the official beginning of attempts that had been growing throughout the state to reforest Vermont. All the while, dairy continued to grow in Vermont, particularly when refrigerated train cars allowed for the shipping of liquid milk, and it didn't need to be processed into butter and cheese in order to be sold. Dairy farms began to modernize with the advent of tractors, milking machines, and bulk tanks. And with this new and often expensive technology, smaller farms began to shut down while other farms expanded. This is a trend that we essentially still see continuing today, and it's interesting to note that the number of Vermont dairy farms has been declining since the 1880s. The 1900s is also when tile drainage became widely used. If you're not familiar with tile drainage, it's a system of perforated underground pipes that drain wet soils, which we have a lot of here in Vermont. So this was a major way that humans began modifying Vermont's hydrology and landscapes all across the state. Today, dairy is still Vermont's major agricultural product, and the main crops in the state are also those associated with dairy, including forages, silage corn, and grain corn. An interesting statistic I saw is that 80% of open land in Vermont is associated with dairy farms, so it's an agricultural product that is still really shaping our landscape and the soils beneath. Since the merino wool craze, many of Vermont's forests have regenerated, and now 80% of Vermont land is forested. Vermont also leads the country in maple production, and that too has its roots in the deforestation craze. When forests were clear-cut in the 1800s, the soils warmed up enough to favor maple when those forests regenerated, giving us a slightly different forest composition than before. I think that's a really interesting way that human actions have influenced soils and the ecosystem supported by those soils. To wrap things up for this lecture, I want to take that land use history and the state factors we've discussed and make note of how these different factors show up in Vermont, influencing the soils that we have. Climate. We have a cool, wet climate that limits decomposition of organic matter, making Vermont soils excellent at accumulating organic matter. That cool, wet climate also makes for slower weathering and soil development and contributes to the relatively young age and lack of development seen in many Vermont soils. In terms of organisms, Vermont's landscape was historically forested, leading to many acidic, highly leached forest soils, even in areas that have since been cleared for pastures. If you've ever dug a soil sample in a pasture and seen that very light E horizon towards the surface, that's a soil remnant of the forest that once was there. In terms of relief, Vermont has many mountains, hills, and valleys. These slopes affect soil drainage, soil thickness, and age across our landscapes. The parent material of Vermont soils is going to depend on where you are. In areas of Vermont that were once covered by the ancient Lake Vermont or the Champlain Sea, the deposits from those ancient water bodies give us valleys that are very rich in calcium and clays. This is very commonly seen in the Champlain Valley, as well as in the Connecticut River Valley. In other areas that may not have been covered by the ancient sea, but were previously covered by glaciers, soil parent material often comes from glacial till, which is the material that glaciers have transported around and then deposited on the landscape. The characteristics of till in a particular area affect both the soil texture as well as soil rockiness. In terms of time, Vermont soils are relatively young because the last glaciers receded about 13,000 years ago. Because of this young age, many soils in Vermont do not show a ton of soil development. And the human factor. Humans have changed Vermont's landscape and soil in some big ways, particularly in the 1800s and 1900s. Our history of draining wetlands and draining wet soils has dramatically altered soil hydrology across the state. Farmland is often in areas that once were forested, so it's somewhat typical to find pastures or hayfields in Vermont with a distinctly forest soil underneath. I'm so interested to see how those soils will develop over the next hundreds of years. Something I also think about a lot is just how much of Vermont's cropland is perennial pasture or hayfields. With good management, these perennial crops can bring a lot of organic matter deep into the soil profile, which could also really influence how these soils develop over time. Thank you so much for listening, and I hope you learned something cool about how soils form. In the next lecture, we're going to talk about the different physical, chemical, and biological soil properties that arise from these soil forming processes and learn about how properties shape soil health.